All right, so welcome back, everyone. So today's our pleasure to have Zaid Harchaoui, who will be talking about heat flows through pre-trained transformers. Yeah, thank you, Zaid.
Thank you very much for the invitation. So I'd like to share with you like some research we've been conducting on transformers, and of course, like transformers are really are still a mystery. It's a very popular architecture in machine learning and AI research. However, it's uh, we don't understand how it really works. And in this project, I'll describe some angle from which we can see transformers and that allows to understand one particular aspect of transformers better. And this is joint work with two fantastic PhD students from University of Washington, Meda Agarwal and Gareth Mulcahy, and a fantastic collaborator, Shumik Pal, also from University of Washington. And so I'll start with the basic engine of transformers, which is the self-attention mechanism. So this is a mechanism that is familiar to many people now. However, it is worthwhile to introduce it just to set the notations. Okay, so what is the self-attention? So it is one particular layer or module of a deep neural network that occurs in many transformer architectures from Llama to many others, and certainly behind popular chatbots such as ChatGPT or DeepSeek, there are many self-attention layers. And so a self-attention layer is a module or layer that's going to take a set of points, x1 to xn. You can identify those with tokens. But in this talk, we'll refer to them as particles due to our framework. And you assume they are drawn from some probability distribution, some measure rho 0 or not. And so um, as you process those particles through the self-attention layer,
Sorry, are you changing your slides? Because there is nothing, we are still in the first
I
page.
am. Oh, I see.
Okay.
Uh, okay, so let me rearrange things. Can you see it? Oh, why is it paused? Okay. See it?
Yeah, we see the first page. Yeah.
Oh, I see, but it seems to be paused. So what is happening? This way.
Yeah. Okay. All right. Yeah.
All right.
Okay. Thank
Yeah. So as the particles are processed by the deep neural network, we perform some linear combinations of the particles and through some attention layer. And what we have is this recursive formula across the particles. And just to set the vocabulary here, this sum is performed with some matrix K that is going to be a nonlinear transform of some cost matrix, which is formed by the product of a query matrix and a key matrix. And those and here the language and vocabulary comes from natural language processing. But for mathematical purposes, it's not really essential. We just consider these as two matrices that are symmetric and square, WQ and WK. And perform this, we compute this cost matrix. It's going to be measure all the pairwise somewhat similarities between the xi's and the xj's. And then we perform a softmax so that this matrix is stochastic, but not necessarily doubly stochastic in the original construction of transformers. And this is what the self-attention mechanism performs. When we look at like large transformers are compositions of a large number of such operations. So we can see transformers as like compositions of many self-attentions with many WQs, Qs, and WKs. And so the question is like, what is this operation performing? And if we iterate this kind of operation, what is the effect of that on the initial set of particles? And this is the subject of this talk. So I'll quickly review like recent work in this area. So it's an emerging area from a mathematical viewpoint. There has been like several works in this area, and they take different angles on self-attention. Um, but the one that really attracted our attention is a really nice paper by Sander from 2022 that defined a variant of transformers that's called sinc-formers. Let me describe what a sinc-former is. So if you go back to the self-attention mechanism, you have this transformation that is performed by transformers, and you have this softmax here, which corresponds to normalizing either, you can see it either as the rows or the columns of the matrix C. And if you look at what happens as you train a self-attention layer with a stochastic gradient algorithm, in the limit of a large number of iterations, those authors, Sander et al. In 2022, have observed that this matrix, after some number of iterations of the optimization or training process, tends to be doubly stochastic in that the rows and the columns of that matrix are normalized. And so as a result, like if we somewhat like neglect or like abstract out the optimization process or the training procedure of a transformer, we can see like the self-attention layer as performing this recursion with a matrix K that is doubly stochastic, and this double normalization, we can think of it as the limit of the sinc-horn NOP algorithm that is very common in optimal transport, in computational optimal transport. Okay, and so what this means is that we can take the matrix Cij and then we perform alternating information projection in order to normalize the rows and then the columns and so forth and so on. And so this is what they call the sinc-former as a reference to the sinc-horn algorithm. So sinc-horn transformer, sinc-former. And this is how we are going to look at self-attention layers and transformers. We're going to look at them through this equation. And so one question is like you take a large transformer, right? Large here means there is a large number of layers, right? A large number of self-attention mechanisms that are plugged with each other, and we compose them, right? And we feed a set of particles as an input to the transformer. It runs through the first self-attention layer and then the second self-attention layer and so forth and so on. And after many, many layers, the initial set of particles may find itself transformed and having a different geometry, a different statistical behavior. And so this corresponds to seeing the transformer and the sequence of compositions that we perform as we run through the layers as an evolution or a dynamical system, if you wish. And the question is, if we look at this evolution of this dynamical system, what is this process doing to the initial set of particles? What is the effect of the processing by a transformer on the initial set of particles? Okay, and so in order to analyze this, we're gonna take a common mathematical approach, which is to take things to the limit. And there are two limits we're going to consider here. One is the limit of an infinite number of particles. So we take the number of particles we had initially as a large number of particles. And then we're going to take the limit of an infinite number of layers. So it's as if the transformer or the deep neural network was a continuum of self-attention layers. Okay, so if we take an infinite number of particles, then the recursion formula for the self-attention layer will write like this with some integral operator associated with the kernel. That is the limit of the sinkhorn algorithm. And then the evolution process will write like this. We take the initial measure rho naught, and then we push it through the first layer with a transform map, and then we keep pushing that measure, the measures through transport maps until we get the k plus 1eth measure. Okay, so now what we want is to write this as a dynamical system or as an evolution. So if we take this recursion formula and we want to write it as a differential equation, what we need is to define a continuous sequence of measures, rho t. And so can write it, we can see this as the discretization of this continuous time evolution. And this way we can obtain the original formula as a discretization of the continuous time differential equation. Okay, one thing to understand here is that the kernel here is defined implicitly because the kernel itself of that equation is going to be the limit of the sinkhorn algorithm. Okay. Okay, so this is the continuous time one, but we can also, when we have finite particles, we can also write the finite particle counterpart of this continuous time dynamics. Okay, so this is the equation we have, and this is the evolution that we want to analyze from a probabilistic viewpoint. Okay, so one question here is if we take the query matrix and the key matrix, what are the conditions they must satisfy with each other? And this determines the shape of the cost matrix and the spectrum of the kernel that appears in this evolution. So here there are various viewpoints on what kind of assumptions we may assume on those matrices. And various empirical observations that have been made in the literature, and it is still a subject of discussion, what are the appropriate assumptions. So in this talk, what I will instead do is just enumerate and survey the various conditions that have appeared in the literature and just focus like like a position at the analysis we've conducted within the realm of all those cases that have been considered. So certainly, like the product must be positive, but then if you look at the value matrix, there are various conditions, and each of those conditions on WQ and WK will lead to particular geometry of the limiting set of particles. And so there are works that have noticed that this lead to like the converging to vertices of a polytope or a union of hyperplanes and others that are a bit long to describe in this talk, but I'll point to the references I will be listing at the end of the talk. And so in this talk, we'll consider this condition where WQ, WK is positive and WV is going to be minus identity. Okay, so let me show how it looks like. So if you take the evolution here and you look at the first condition, as the particles evolve through the layer. So again, like this is not the evolution of the particles during the training. This is after training. If you take data and you pass it through the network, how the particles evolve through the network, how the neural network processes the particles, right? So it's the input-output map, if you wish. Okay, so you take the particles and they will scatter over time. So that is across the layers of the deep neural network and converge to the extreme points of a polytope. So this is the first case. The second case is the particles will converge to a union of parallel hyperplanes. Here, there's just one hyperplane, right? So they converge to a low-dimensional manifold. The third case, the particles will evolve over time, and they will converge to a subspace. And the third one, the tokens will progressively scatter across space, but without a particular, like say, singular geometry of the limiting cloud of particles. Okay, so what we show in this talk is that in this particular case, when we consider WQ, WK positive and WV minus identity, then we can show that the discrete process, that is like the process that is represented by a finite number of layers of a deep neural network that has as a basic component a self-attention, as we take epsilon to 0 and time to infinity, then the process will converge to the solution of the heat equation. Okay, so this is how it looks like as we converge. And when the process we're going to specifically analyze is this one. Okay, so the key tool we're going to introduce is the so-called barycentric projection. So if you look at a single particle and you pass it through a push-forward map, uh, and you obtain another particle. This is the process that we are all familiar with in statistics. This is called what we use when we do regression, right? So you take an x and you pass it through a function, right? And you get a y, right? When we try to learn a function from data, what we try to model, we model it as a conditional expectation that is a projection. When we have measures, we have an analogous concept. The map, the push forward map that takes rho epsilon k onto rho epsilon k plus 1 is going to be related to what people have designated in the literature as a barycentric projection. So this barycentric projection is what encodes a push forward map from rho epsilon k onto rho epsilon k plus 1. And the barycentric projection can be obtained by solving an entropy regularized optimal transport problem. And so we use this construct to take rho 0 and displace it onto rho epsilon 1, onto rho epsilon 2, and to rho epsilon n, and so forth and so on. The issue is that this particular process is very hard to analyze. It's very hard to analyze, and in order to analyze it, we need to use an approximation to analyze this process over continuous time. Okay, and so what we can prove is that as epsilon tends to 0, if we look at the continuous time trajectory of the process, it will converge to the continuous time trajectory of another limiting process, and this process is the solution of the heat flow equation. So when we describe this limiting result, so it's an asymptotic result, there are a few observations to make. So one is that we have very little understanding at this point, whether it's in this work or other works, on the rate of convergence of this limit of this limit. We know very little of like Is this like a fast convergence rate? Is it a slow convergence rate? And so forth and so on. The other thing is that the only tool that allows us to, so far, to obtain such limits is weak convergence, right? So like functional limit theorems. And there are very few tools actually to analyze this process. But still, what this indicates is that as you compose self-attention layers a large number of times, there is a simpler process that describes the effect of this large number of composition of a self-attention layer. Okay, and so in order to analyze this limit, what we need is first to like describe what this equation means, right? Okay, so I'll do a short intermezzo on entropy regularized optimal transport to have, on the one hand, lay the groundwork for our results, but also to popularize this tool for the analysis of this kind of process. Okay, so in optimal transport, what we do is we have two measures, and we're trying to learn a map that maps one measure to the other. And the classical optimal transport problem solves an optimization problem where we're looking for the transport plans between some measure mu onto nu. And we do not add any regularization to solve this optimization problem. A famous theorem by Brenier gives a solution of this problem as the gradient of a particular convex function and gives a gamma star as a solution to this problem. Here, W2 corresponds to the Wasserstein distance. In entropy regularized optimal transport, what we add is an entropy regularization. And the solution of this problem is going to be the so-called Schrödinger bridge. It is also, it can also be related to this is something that can be approximated by the Zinkornop iteration. It has been popularized by Couturier and Perret. And so when we solve this optimal transport problem, right, which allows us to map mu onto nu, right, what we're taking is like x that is drawn for some mu and y that is drawn from nu. And the coupling between the two can be represented by this functional that is called the barycentric projection. So I personally find that it's not a particularly appealing name, except for like drawing an analogy with the condition expectation when we do regression. But the important thing here is that the expectation is under the Schrödinger bridge from mu to nu. Okay, and so basically, when the summary of this is that when you take a measure mu onto nu, and in our case, we're going to take this between the measure before a layer, before it passes through a layer, and the measure after it's passed through that layer, right? So this mapping can be modeled by this barycentric projection map up to an identity operator and some multiplication constant. So the map between the entry, the input of a layer and the output of a layer is going to be identity minus 2, the barycentric projection. Okay, so now that we have this construct, which is the barycentric projection, we can write the map between as we pass through the layer, and we read like this. It's going to be two identity minus the barycentric projection, which is this map. And notice here that it's the Schrödinger bridge that we are using here. And it takes us from rho at the kth step or layer, if you wish, to rho k plus 1 at the k plus 1 layer or step. So one thing that is important here is that for the self-attention layer, the Schrödinger bridge we're going to take is the Schrödinger bridge that is between two distributions which have the same marginals. So this is a bit puzzling, but recall that self-attention is a self-attention layer, right? So it is comparing using all the self-similarities of a set of particles with itself, right? And the transformation that is applied by the self-attention layer uses the couplings of that distribution of particle onto itself, right? The map of course transforms the set of particles, but it relies on that. Okay. Okay, so I skip that. Okay, so the first result we have is that when we take this evolution process, what we can do is approximate it by a diffusion process. And the diffusion we use is the Langevin diffusion. So the Langevin diffusion is a diffusion that has two components. One that is corresponds to a Brownian motion or a Wiener process, and a drift that is driven by a gradient, the gradient of G. And as a result, we have a process that has these two components. One is purely stochastic, and the other one that drives the process in a particular direction. And then if we look at the law of that process, and we want to compare the law of that process to the law of the Schrödinger bridge, we can control the error of the two process by using an entropy. And we have a somewhat exact inequality where we take the difference, the two entropy, like from one to the other and the other to the one, and we can upper bound that exactly in terms of epsilon. So what this allows us to do is that we can replace the Schrödinger bridge that we have in the previous formula with the Langevin diffusion. And the Langevin diffusion, you can think of it as somewhat of a, it's very abusive to use this, but you can think of it as a kind of tangent process of the Schrödinger bridge in a small time limit. And so it is an approximation process to the Schrödinger bridge. So in other words, like we have our continuous time process. Every time step we can describe by a Schrödinger using a Schrödinger bridge, and then each of those Schrödinger bridge we're going to approximate by the Langevin diffusion, and this allows us to like then fall back on like results we can use from limiting functional limit theorems. Okay. All right, so now if you take a particular density and you make it and its its evolution is described by the solution of a heat equation. If you consider the following ODE, where you are the time evolution of xt is driven by minus the gradient of the by the score of rho t. Then the evolution of the process is going to be very easily described by this driving term, which is the score. Okay, so the key result of our paper is that if you look at the barycentric projection, it can be approximated by something that is very close to the score, up to the identity map. So in other words, if you look at like the same marginal coupling we make that we use to describe the process of the self-attention layer, this map we can relate it directly to the score of that is the derivative of the log of the measure. Notice here that this is quite inspiring if we look at what people do for diffusions, right? For generative AI, one of the key challenges when sampling using diffusion process is how to approximate the score. So what we show here is an alternative viewpoint where actually we can approximate the score directly using a same marginal Schrödinger bridge. Okay, so this is the first one key formula that we prove in this paper. And then thanks to that, what we can do is that we can take our process and take the process that is we build piecewise by using Schrödinger bridge and show that in W2, those two processes are closed. So if you look at so this is the process using the Schrödinger bridge, and this is the process if we were to use a classical discretization, such as the Euler discretization. The downside of using the Euler discretization is it requires the knowledge of the gradient of the log of rho. But one thing that is great with the Schrödinger bridge is that it kind of bypasses the issue of knowing the score and gives you the same level of accuracy of approximation of the process as the Euler discretization. Okay, so thanks to that, we can prove that uniformly the two processes are close. So this is an asymptotic result. Like for this, what we do is like we approximate the process on every time step using the Schrödinger bridge or using the Euler update, and then we integrate over the whole trajectory of the process, and then thanks to that we make the time step converge to zero, and we obtain the convergence of the two processes. Okay, so all right, so now yeah, so that's what I was describing. So the first thing is that if we take a little time step, we can control the error of the explicit Euler scheme, and then we can also show that as the process evolves over time, it does not diverge, it contracts, and thanks to that, we can control the full trajectory of the process. Okay, so now I'm going to show a few simulations. So if you take, say, a mixture of Gaussians for the particles, so you take a distribution of particles that is bimodal. So on the one hand, you have a Gaussian that is like kind of tilted to the left. On the other hand, you have a Gaussian that is on the right. And then you take the particles sampled from the distribution and you pass them through the neural network that is composed of self-attention layers. What you can see is that as those distributions run through the layer, so T here corresponds, you can think of it as like passing through the self-attention, every self-attention layer of the neural network. What happens is that the distribution kind of melts, right? Over time. So as there is an intermediate time step where somewhat the distribution is kind of like unimodal, so the two modes have melted to such an extent that they are kind of like confused with each other. And over time, like the entire structure of the data of the distribution was completely melted. So what is interesting here is that if you look at like if you look at a large number of steps, then in that scale, of course, it looks like as if applying the many self-attention, there's a trade-off, right? Like there is a point where somewhat the distribution is less singular and still has some content, and there is a point beyond which the entire structure is like somewhat completely melted. Uh, so so I'll yeah. So uh, this just to summarize like the work. So what we have shown is that if you take a process that you usually describe with the Euler discretization or another discretization, so it could be the JKO discretization, which is implicit. What you can do is you can like, approximate every step with a Schrödinger bridge with same marginals. And then once you have the Schrödinger bridge with same marginals, itself can be approximated by a Langevin diffusion. And then you can analyze the process in continuous time. And so this gives, for processes that correspond to dynamical systems on measure, a technique or an approach that allows you to analyze this process by relying on tools from optimal transport. And it's an alternative to approaches that are based on JKO schemes or like proximal point schemes, which usually see this as a gradient flow. But gradient flows, when require usually the construction of geodesics and other geometrical constructions, which may not be tractable for many processes. So here we can bypass all that just using the Schrödinger bridge. So I'll end here, and I thank you for your attention. And so this is a preprint, and there have been various presentations in workshops and conferences. And there's also code to reproduce the little simulations we have made. And as future directions, we are looking at like mean field limits of a similar process. We're also looking at the backward process. Here we looked at the forward process. We could also look at the process when looked from the output to the input, right? So the reverse time process. And finally, like when we took the infinite number of particles, but there's also the question of like if you take a finite number of particles and you make the number of particles grow to infinity, so what is the error you have when you do that, and how can you simulate this process using particle approximation? And I'll end with some references to also, like share my enthusiasm in other works. So this is the Sander paper by Sander, Ablin, Blondel, and Perret, which inspired this work. But I also point out two other papers that I found very inspiring. One by Vukovic, Baratin, and Taché-Descombes in 2020, which may have been like the first mathematical analysis of self-attention and transformers. And also a recent work by Castin, Ablin, and Perret which has a more variational viewpoint on self-attention and transformers. Thank you.
Yeah, thank you very much. Any questions or comments? Yeah, okay, seems not. Maybe it went too fast. Yeah, okay, so maybe not. Yeah, so maybe I just have a general questions. I mean, this kind of techniques can they be used? Okay, here's a question. Yeah, Carl, do you want to unmute yourself? Yeah. Yeah. Okay. So yeah, someone is asking me on the chat. How about the scalability of the proposed approach, and is there any guarantee boundary?
The scalability with respect, so yeah, this is a very interesting question, but like with respect to what parameter? Uh,
Yeah, Carl, can you unmute and ask directly?
oh,
Yeah, he's writing on the chat. Yeah.
oh, yeah, I see. OT can be very challenging. I mean, I guess you mean like optimal. Okay, so let me rephrase the question. I guess you mean because we approximate the process using optimal transport, then the actual approximation would rely on solving optimal transport problems, which scale quadratically in the number of particles, and therefore may not be scalable. Yes, it is true, but well, in this paper, we do not. The reason why we introduced this barycentric projection and the approximation of the process is for mathematical convenience, but not for computational purposes, right? So it is not. So the approximation process we propose is at least like in this current shape is not intended to be like computationally attractive. It is more analytically attractive in that it facilitates the analysis.
Yeah. Okay. So he's happy. Any other questions or comment? Yeah. Any guarantee boundaries? Any guarantees boundary?
Yeah, so I'm not sure I understand that question. What does it,
Yeah.
what do you mean? What do you mean by guarantees boundary? I'm not sure.
Yeah.
Ah,
Generally.
oh, I see. No,
Generalization boundary.
I'll be completely honest, I have no idea what I think why self-attention works in terms of generalization is a fascinating question from a statistical viewpoint. But yes, I have no insight on that at the moment. I think a promising direction is to relate self-attention to kernel-based methods. Um, but that's all I can say. I mean, I don't think there has been concrete progress in this. I'm not aware of a concrete significant step in this direction yet. Except for, I think, if you assume that uh, self-attention and the transformer is trying to recover a very specific dependent structure in the data, then such as like when you're trying to do reasoning or when you're trying to solve the parity problem or things like that, then you're operating in a setup which can be somewhat like related to sparse recovery, right? Because you're searching a space of many connections, and you're trying to learn something that has a very sparse uh, set of connections across layers and among particles. Uh, then there has been like very nice works in this area by Jason Lee and his group and so forth and so on. But like it is that aspect is very different from here because if you look at those set of assumptions here, right? Um, or like sorry, let me show you. It would correspond to like assuming that the data generating process comes from a Cij matrix, which may have some kind of like eigenvalue pattern or like sparsity pattern, specific one, and that this, when you learn the self-attention layer and the transformer, you're trying to recover that sparsity or like pattern or eigenvalue pattern. And so it's a very interesting area of research, but it's you know it's you require tools that are quite different from the ones described in this talk. Very nice question.
Other questions? Yeah, all right, thanks. Yeah, actually, my question was related to what you just said, which is how would you see the application of kernel methods in this kind of context?
So
Do you think about just like transforming as a like featureizing everything, and then yeah, I don't know. I'm just guessing. Yeah.
well, I mean, there are two ways to look at this, right? Like there's one is like you take transformers and notice that you know this K is not very is kind of a kernel matrix, right? And you're trying to import IDs from kernel methods like Nystrom and like all large scale kernel machines, you know, like IDs that have been developed. So that's one, and I believe like there has been works on like linear time transformers and things like that, including by Sanjeev Kumar at Google and his group. And there is another viewpoint, which is like currently in transformers, people use a lot what they call MOE, which is a mixture of experts. And what mixture of, so they interleave a mixture of experts in the architecture. And this allows them to scale and also have like better, like have be more parameter efficient. And what those mixture of experts do in terms of like kernel viewpoint or even like optimal transport viewpoint is very unclear at the moment. But I do think like it's a very interesting question, and like trying to mathematically analyze like what MOE do. Well, you know, MOE have been extremely popular both in industry and in research. But what exactly do and why they even work, I think it's a very interesting question.
Okay. Yeah. Thank you very much. Thank you. All right. Any last comments, questions? All right. Yeah. Seems not. Yeah. Thank you very much, Zaid, for the nice talk, and thanks everyone
Thank
for
you.
coming. And yeah. Yeah. So which one?
Uh, uh, oh, MOE. So I mentioned about attention. So I mentioned.
Yeah,
Can
we
you?
don't. Are you on the screen? We don't see
May I
anything.
suggest that you send me an email? I can follow up via email if you don't mind. Yeah.
Okay.
Carl. Yeah. Thanks. Yeah. I'll be
Yeah.
happy to follow up by email.
Yeah, I'll upload also the talk online, so maybe you can just also play it slowly. All right. Thanks again, Zaid, and thanks everyone
Thank you.
for coming,
Thank you very
and see
much.
you soon. Yeah. Okay. Take care,
Yeah.
everyone. Bye. Bye.
Bye.